We wanted to build a building that stood out in a world of global buildings.
The great engineers that I love working with come up with ideas that we've never heard of before. And on Wilshire Grand, we have some solutions that we had no idea we were going to get into.
On a tall building like this that extends up to 1,100 feet to the top of the spire, there are factors as an architect that we would never have considered.
It's the biggest, best, most challenging building that I've ever worked on. It's had so many exciting things in the design. It's had so many problems that had to be solved, had so many sleepless nights.
In order to support the load of a multi-story high-rise building, a special foundation is required. Two world-class structural engineering firms designed the structural system for the Wilshire Grand. Thornton Tomasetti was involved in the seismic design, and Brandau and Johnson structural engineers were the engineers of record.
The very first thing that David and I and our engineering team struggled with was the slenderness of a hotel tower that was also going to be 1,000 feet tall. So, seismically active area like Southern California with a foundation that's going to be about 100 feet below grade, we needed a very large mat foundation.
It's the size of a football field. It's about 270 feet long, 140 feet wide, 18 feet deep.
The base of the 1,100-foot Wilshire Grand Tower is a critical point of load transfer. The forces come to rest here and are transferred to the soil below. In the Wilshire Grand, the mat foundation had to be poured in a single concrete operation to avoid cold joints, which would have led to crack points in the foundation.
We had to make 2,150 concrete truck deliveries in 17 hours. So we booked every concrete truck we could find and we poured the foundation.
We knew ahead of time that we had to come up with a project-specific thermal mass concrete cooling plan. As a result, we came up with a system where we injected, while the concrete was curing, 680 tons of chilled water to assure that we did not crack the concrete in the 18-foot thick mat foundation.
We put in 19 miles of cooling pipe inside the mat footing because of heat of hydration of the concrete. So we put thermocouples inside the concrete at the center of the slab and at the edges. So we monitored the temperatures in that slab for about 2 weeks. And we made sure that the core temperature never exceeded 165 degrees, and we never had more than a 35-degree differential between the inside and the outside edges.
Los Angeles is a city built on the infamous San Andreas Fault and thousands of other earthquake faults. The Wilshire Grand Center sits directly on one of these faults and is also a very slender high-rise building, which makes it unique compared to other buildings in downtown Los Angeles.
We were fighting two things. We were trying to get a building that was stiff enough for wind design and a building that was strong enough for seismic. So by making the building too heavy, it makes it better for wind, but it makes it worse for seismic.
A key part of designing a tall building like the Wilshire Grand in a high seismic zone is what's called performance-based design. So that means taking a computer model of your building and running it through a series of simulated earthquakes. When the ground shakes, all different vibrations travel up and down the building. and you'll be able to see all these behaviors in the model analysis. The speed is about 1/6 of real time, but you can see now waves kind of traveling up the building. It's not a big old lateral one-way sway. You can see the top of the tower, the sail kind of jiggling a little bit. It's seeing more acceleration than at the bottom of the building. So this looks like a lot of movement, but it's because we've exaggerated or amplified the movements by a factor of 50. If we did it to accurate scale, it would look like nothing was happening at all. The real building will not move like this. The appropriate earthquakes to use for a building depend on the faults that are nearby and those that are far away but may have very large events. A distant fault will kind of make a rolling motion at the site. A nearby fault will make more of a sudden jolt. And those were all folded into the 11 sample earthquakes that we used to test the building.
Earthquake and wind design is the specialty of structural engineers. Architects and engineers collaborate to choose an efficient lateral force resisting system.
The decision was made based upon a lot of very good thought, that it was a concrete core with a steel frame. The advantage is that the concrete core would slow the sway of the building down in an earthquake.
Concrete core means, as you might expect, the walls are made of solid concrete with a lot of reinforcing bars inside. The reinforcing bars are helpful to hold the concrete together in a big shake.
The concrete core weighs approximately 133 million pounds, or 65,000 tons, and provides the central structural system that resists the lateral loads. It is the main focal point for the earthquake and wind resisting system.
Perimeter steel is steel columns filled with concrete. And then supporting or rather balancing the core against the perimeter frame are BRBs, buckling restraint braces.
In order to make the building stiffer, we had to put outrigger columns on the outside edges of the building and attach those columns with braces to the core wall so that we take the overturning out in the edges of the building instead of just under the footprint of the core wall. So it's really amazing how much stiffer it made the building by putting in those braces. And then on the outrigger box columns, they're between 1.5 and 2.5 inch steel plates that are 34 to 58 inches in plan view. And we filled those with concrete to make them stiffer.
So this allows the building, which is very slender in one direction, to be able to take the wind loading and the seismic loading on a daily basis, really. I mean, we have movement that occurs regularly.
But the challenge was, how do you marry those two different systems together? And maybe one of the most inventive parts of this.
One of the problems that we had on the Wilshire Grand project that seemed almost unsolvable was the incompatibility between the concrete core and the steel structure.
Concrete and steel are two very different materials. Blending them into one structure creates challenges that involve thermal movement, dynamic response, and long-term shrinkage.
When you integrate these two types of systems, you have this very complex assembly, knowing that the concrete core that takes most of the shear from a dynamic seismic event, that the concrete will shrink as just a normal, natural process. It cures for 50 years.
The core wall gets shorter. It can get as short as 8 inches shorter than the rest of the building over time. So what that does is it pulls on all the braces, it pulls on the belt trusses.
So that's 8 inches, not
vertically.
Over the whole
8
height.
inches over 100 years, the top of the building. But because of the BRBs being attached, that 8 inches is a smaller number. It might be around 4 inches.
Structural engineers and architects solve many design challenges. These attributes define the Wilshire Grand among its neighbors as a distinctive high-rise building.
The vision that the structural engineers knew that was the number one challenge in building tall, and how we addressed it was probably one of the most successful challenges on this job.
Over the course of a year, just, worked out a solution for that. And it was a combination of things. It was the buckling restraint braces. It was putting in shrinkage-reducing admixtures in the concrete. It was timing the way we attached the braces to the building during the construction of the project. And it was also doing something that's never been done before on a building, and that's pre-compressing the braces in the top of the building. We compress them about 3/4 of an inch, and then we install them into the building, and then they let the jacks go, and then it lifted up the floors from 70 all the way down to about 55. And at the top of the building, the floors came up about 1/2 of an inch, and then incrementally a little bit less each floor.
Really?
Yeah.
And so the outside perimeter columns are currently in tension.
Yeah, all the outside building columns are they're in tension. They're hanging from the top of the building right now.
Like every building, the Wilshire Grand started as a dream. Teamwork turns dreams into reality. The Wilshire Grand Center stands as a perfect example of how art met science to forever change the Los Angeles skyline.
It was a challenge to develop a system that met all the requirements for the architecture and for public safety, and to have it all come together so beautifully.
It makes me feel proud to be an engineer. I mean, it's really an amazing accomplishment to see such a tall building in downtown. It's also one of the first buildings downtown that doesn't have a flat roof. So it's an iconic building. It'll be around for many years to come, and it'll be the crowning achievement of my career.
The building really has a different characteristic in sunshine and in a cloudy day, a rainy day, a day with snow on the mountains. So I think there's a dynamic to the building and the composition, and I think that's important. We worked very hard to work with the fire department to look for alternatives to the flat top helipad. So we did it, and then the next generation of high-rise, they're gonna have the freedom. I feel good about starting that trend.